We were looking at some other ways of making logic gates. That is, we were trying to control the current source at the bottom of the differential pair. We were trying to control the tail current source. So we have logic input A applied to the differential pair, and we said somewhat vaguely that we can also have some logic input here. Now, this being high means the differential pair is activated and the output will be related to the logic of A. Okay. Of course, when this is low, there is no differential pair and the circuit is not functioning. But we can get a functioning circuit if we have another differential pair which works complementary to this. Okay. So let's not worry about what voltage levels constitute logic of B and B. Okay. We connect these two together. Now, regardless of the logic state of B, we know that current is flowing through one of the two differential pairs, right? So either this is active here or this is active. So there is no problem. The output will be respond to either A, or let me call this CP and CN. It will respond to C. Okay. And the logic function was what? AB plus C times B bar. Okay. Now, what should be the logic? What should be the voltage levels of B corresponding to logic level 0 and 1? That is, okay, first let me go back a little bit and discuss what we've already done. What should be the voltage levels of AP and AN for basically 0 and 1? How do you decide how much voltage to give? VDD, AP and AN. No, I mean, no, I'm not asking what is it, like what should it be for the proper operation of the circuit. Huh? And the other one? VT plus 2 times VD sat. What is that? That is the lowest limit, right? On what? So, okay, what is the logic state of A determined by? Is it the voltage of AP and AN or something else? It's the difference. It's the voltage difference between AP and AN. The absolute value matters to the extent that the circuit should be functioning in the right region, but it's not very critical, meaning there is a range of values of AP and AN both. You can shift both of them up or down, it will still work as long as the difference is appropriate. So if AP is sufficiently positive compared to AN, it will be one logic state. If it's sufficiently negative compared to AN, it will be the opposite logic state. The absolute value has to be some level so that, for instance, this transistor doesn't go into triode region and this doesn't go into triode region. Okay. So these two should be in saturation. But within that there is a range. You can move both the AP and AN up or down as long as the difference is maintained. The logic level in interpretation of the logic does not change. Okay. So it's the difference that determines the logic level. So this is the sense in which I am asking the question: what determines the logic level? What determines the logic state of B? What are the voltage levels we need? I mean, is it the absolute values of BP and BN, or is it the difference? What is it that we want? Absolute values. And what should the absolute value be? Okay. So lower level is 0, that is pretty trivial. If one of the gates is at ground, then clearly this is inactive, right? What should the higher level be? VD sat. What is VD sat? Okay, what is VD sat here? VD sat of what? No, the drain voltage is not VD sat. Right? Yeah, but VD sat is a function of what? The current. At what current are you calculating VD sat now? See, the VD sat is something, if you bias it at a given current, you can say it is the VD sat is this much and that's the voltage for it to be in saturation. But now the current itself is determined by the voltage at the gate. Okay. So what voltage will you bias it at? What is the voltage you will bias it at? Any voltage which maintains it in saturation. Is that a good idea? What happens if this voltage changes? Current will change. So, yeah, no, constant current through the supply, that's in a different sense that we talk about, right? We talk about constant over time, right? That doesn't really say anything about how much the current should be. It only says that the current should be constant over time. Depends on biasing value of what? No, okay, what determines the current in the circuit? Yeah, so what, like, okay, if I wanted to, let's say each of these, I mean, when this is swung to one direction, the current flowing through here is 100 microamps and this is 0. I want to change it to 200 microamp. What would I have to change? What is the, like, where is the variable that determines the current in this? Huh? M naught. R. What bias voltage are you talking about? Which bias voltage? So, it's the voltage that you apply here that determines the current, right? It's not really operating with a fixed current in that sense. It's whatever voltage you apply here, that changes the current. So, if the voltage is in error, the current will be in error. What's the consequence of that? The swings will be different. You assume some output swing for this one. So, that will change. So, you may not be able to drive the next stage very well. That is one issue. So, not to mention, see, one advantage of digital, the biggest advantage of digital circuitry is noise margin, right? One of the advantages, the primary reasons why you use digital. That means that if the voltage representing logic 1 differs by some amount, the operation of the circuit should not change in a big sense. Now, that is not the case. We are saying that for this to be interpreted as logic 1, it has to be some fixed value, okay, equal to this, where I naught is the current we desire in the circuit, okay. No, I mean, I naught depends on this voltage value, right? Yeah. So, is that what you want? Yeah. Yeah. So, no, this is like you're confusing cause and effect. This voltage causes the current here. It's not that this current causes the voltage, right? Yeah. So, basically the current is dependent on the voltage level corresponding to the logic. Is this something that you would like? Like, what is the idea of a digital circuit? Like a certain range of voltages should be interpreted as voltage 1 properly without the operation of the circuit changing. Okay. So, now the current is directly dependent on this. It goes through square law if the transistor is obeying square law. And so, the output swings will change depending on VBN. Okay. That is certainly not something you want, because then driving the next stage may become difficult. If the current becomes too low, it may not switch it. Okay. That is one thing. Huh? Okay. What happens if the current is very large? You are saying there is only a lower limit, not an upper limit, right? Yeah. So, it is definitely there. And also, as you change this current, the common mode value of the output also changes. Okay. What is the common mode of the output? VDD minus? So, this is the average value between these two. Okay. Yeah. So, basically, see, what happens is now the current is dependent on the tail source. So, the output common mode and the output swing, everything changes. So, this is not a desirable situation, because when you have a bunch of these circuits, you may not be able to drive the next one properly. Okay. Yeah. So, what you want is not something like this, but the current should be some fixed current controlled by a current source. Okay. How do we do that? So, these two are complementary logic levels. So, we do the same thing like we have done for the upper pair. Okay. So, instead of doing this, if you do this now, what is the voltage level corresponding to logic 0 and 1 of B? Here also it is only the difference that matters. So, this also ties in with the philosophy of using differential signaling. It's only the difference that matters, not the absolute value. Okay. So, it's also resistant to any common mode noise and all of that stuff. Okay. So, this is how we need to do it. So, now this does implement this function where A, B and C all are differential inputs. Okay. Is this clear? Is the problem with the earlier arrangement clear to everyone? That if we ground this, then the current is dependent on the absolute value of the logic voltage. First of all, it may make the logic circuit non-function properly. The output swing may be too small or too large. In either case, it may have problems like driving the following stage. Okay. Range of detection. Why? Why will it be reduced? What is the voltage swing here? You mean the output voltage swing? What is the output voltage swing in this case? What will be the output voltage swing? Basically, by voltage swing, I mean, what is the difference between output voltage corresponding to logic 1 and output voltage corresponding to logic 0? What is that? How much is that? 2 I naught R. It's the same thing as before, right? It is not changed at all. It depends only on I naught and R. Yeah, actually that is a very good point. So we'll see how to drive the lower inputs. Okay. So this is the input C and this is the input B. Okay. Now assuming all transistors are in saturation, what happens is, let's say if BP is more positive than BN, this is a current I naught, then I naught can flow either here or here. Okay. And if it flows here, depending on the state of A, it can flow either here or here. And if it flows in this, depending on the state of C, it can flow here or here. So that's how you get that multiplexing logic. Okay. Now, we said that everything is now determined by the differential voltage. Of course, that doesn't mean the common mode can be absolutely anything. Usually that means there is a certain range. So let's evaluate what the range is. So, common mode limits. Okay. This whole action works very well assuming all transistors are in saturation under all conditions. Now, what is the limit for the common mode of B? Is there a limit? Is there an upper limit? Is there a lower limit? Firstly, what happens? Let me label the transistors. M1, M2, M3, M4, M5, M6. I am not going into triode region. Yeah. So, the common mode voltage of B should be high enough that M0 remains in saturation. Okay. Is there an upper limit? Cutoff, sure. Cutoff, definitely. What about, can it go into triode region? Oh, what were you saying anyway? How is it related to cutoff? Is that possible? I mean, I am assuming that the differential input is large enough to switch one of them. Okay. Okay. So what is does it impose any limits on the common mode voltage of B? I mean, just think about what happens if everything else remains fixed, but common mode of B is going up. Yeah, M1 or M2 will enter into triode region, because if everything else is fixed, the voltage at these points X and Y, they are fixed. So if you keep on raising BP or BN, it will eventually hit the triode region. Okay, either M1 or M2. And what is that value? VDD minus I naught RD minus VD sat M4 minus how did you get this?
We have to take into consideration when the
okay.
So for that we have considered that the total current is flowing out.
No, this is all fine. Okay, this part is fine. I only have a question about this. How did you get this? Yeah. See, the VD sat is something that is a limit on the drain source voltage of the transistor. It's not the drain source voltage that you see all the time, right? So it doesn't have to be VD sat. Okay. So the condition is something different. It should depend upon common mode of A and C, right? Let's assume A and C are the same because they are the same logic level. Okay. The minimum voltage at X and Y should be such that a minimum voltage, it is related to the minimum voltage at X and Y and the maximum voltage at B. Okay. The maximum voltage at B is such that when X and Y are at their minimum, these two are still in saturation. Okay. So first limit was, okay, this is just the lower limit, and what is the upper limit now? Minus 81. What's that? Yeah. So anyway, I mean, it's not necessary to remember this. It's only necessary to remember the condition under which it happens, right? After that, just by looking at the circuit, you can write it down. So given common mode voltage here, there is a limit on how high you can take VB, right, the common mode voltage of B, and that's dependent on M1 and M2 getting into triode region. Okay. So the question is now, like coming back to what he said, can the common mode of A and B the same? Can the common mode of A and B be the same? If what happens if common mode values of A and B are the same? Huh? What happens when if the common mode values of A and B are same? This thing is clearly not satisfied. Okay. So the common mode value of B must be less than the common mode value of A. Okay. So clearly the same circuit cannot drive both of these. So we have to make some arrangement to lower the common mode value of B compared to the common mode value of A. Okay. So what can we do? So firstly, what is the difference that is required? Actually, if we assume that VT1 and VT3 are the same, then VD sat3 is the difference. Basically, roughly an overdrive difference between the two common mode voltages. Okay, that's what you need. Now, VT1 and VT3 will not be exactly the same and so on. So all those details can be taken care of in simulation. Okay. So let's say that we don't care about like maintaining this optimum difference. We want some difference, okay, which is more than this. How can we do that? Huh? Common source. Why? Source follower. Okay. So we need a level shifter. So let's say we have the circuit where A, B and C come from the same output. Same output meaning some other logic like this. Okay. A and B and C are outputs like this. So then A and C can go straight into the circuit. For B we need to have a level shifter. Okay. So at the risk of messing up this thing, let me. Okay. So now you can apply the same common mode level to A, B and C, and the logic is the difference voltage of AP and AN, BP and BN and CP and CN, and the whole thing will work. Okay. And there is also an upper limit on these things. There is an upper limit on the common mode of A and C, and it's the same as for any other source coupled logic. For a single inverter or a buffer, we evaluated the upper limit on the common mode value of A. The same thing holds here. Okay. So if A rises up too much, then M3 can go into triode region. Okay. Yeah, what's the problem? You tell me. What might be the problem? Yeah. So, okay. Let's just look at this itself. A single gate. Okay. And you want to use this as a switch. And I say that the transistor should be in saturation. Of course, it's a switch, so one of them will be in cutoff. But the on transistor should be in saturation. What would be the consequence if it's in triode region? What's that? Or, it's okay to have it in triode region. Yeah, there can be a larger transition region. So what happens is, see, as you keep raising this, if this goes into triode region, then firstly there will be, this node will move by a lot more. Okay, that is one thing. And then if this moves by too much, actually I don't know if it can move as much as pushing this into triode, that is possible. So if these transistors are in triode region, you will need a larger voltage to switch. That's the disadvantage. And that is the same thing for the lower pair also. Okay. Yeah. Yeah, what was the condition to avoid that? So you are saying if this is at VDD and this point is at B. Oh, this one here. So if this is at VDD and this is at VDD minus IR, it will get into triode. Why will it? What was it? Yeah. A is at VDD minus IR. Okay. So if A is at, you mean A meaning AP or AN? Doesn't matter because it's only the on transistor that determines the voltage here. Okay. So see, by putting these level shifters, we have satisfied this. In fact, we have done more than this one. Okay. What is the actual VBCM in this case? I mean, this VBCM refers to the common mode voltage at this point, okay. That's what we calculated. So what is it in this? I am saying the common mode voltage of this and this are the same, okay. What is the common mode voltage here? Minus VT. Minus VT minus VD sat. So in fact, all we need is a difference of VD sat, but we have a difference of VGS. In fact, we have met this condition by a lot of margin, okay. So in this case, that won't happen. So the question was, when BP is in one direction and AP is in the opposite direction, what happens? But the voltage here is not determined by the lower of AP and AN, it's determined by the higher of AP and AN. Okay. In fact, the worst case is when AP and AN are crossing each other. When AP equals AN, then that's the worst case. That's the lowest voltage that you see here. So you can also evaluate the limit on VDD like this. So obviously, as you go on reducing the value of VDD, something will go into triode region. So there is a minimum supply you need for this circuit to operate, and like for any other circuit that you can evaluate by just adding up the different conditions. Okay. So we have some circuit which is a multiplexer and which can be driven by other similar logic gates, that is this current mode logic. So let me put the source followers in here. So these are the B inputs. Is it visible there? Okay. I have source followers in front of B. Now if you want a larger swing, what was the condition for this to operate? We said that I times R should be smaller than VT, okay, because the higher level here is at VDD, and under those conditions this can be at VDD minus IR, okay. So for this to not go into triode region, I times R must be smaller than VT, and if it is larger than VT, for some reason you need a larger swing than that, then the only way is you put more level shifters. So you put level shifters in front of this, in this, and also this B, okay, right. So A will have one set of source followers, C will have one set of source followers, and B will have two sets of source followers. So if you level shift everything, of course everything will work the same. Then you can increase the swing. But with the present day logic voltages of 1.8 volts and less, typically you don't have that. You have only one set of followers. Now there are other ways of level shifting. You don't have to use voltage followers, because, especially because this is an over design. We wanted a common mode difference between A and B equal to VD sat, but this will provide a difference equal to VGS. So you can use some other scheme to level shift it by something less, okay. And also we'll see a bunch of cases where A and C come out of some logic signals, whereas B comes from some other circuit. So you can adjust the common mode of that circuit independently of A and C, okay. Any questions? So we have a multiplexer which realizes this, and one of the things that we needed for our serializer was the multiplexer. In fact, the serializer was built around the multiplexer, and you can use this circuit to do that at high speeds, okay. At very low speeds, of course, you can use CMOS gates. And the key here is every signal is differential, like all three inputs and the output, and also the current through the supply and ground is a constant. So one thing is, so let's first imagine an extreme case where when AP and AN, when they're okay, let me not do it like this. So let's say this is the positive input, this is the negative input, okay. So we want this to switch when the difference between VIP and VAN becomes something, and okay. So let's say which is the easiest case. So when both are in saturation, always we have worked out the relationship. The two currents, I1 and I2, they will do this, okay. So if this is I0, when the input is 0, they will be equal to I0 by 2. So this is what happens, right. And at some point the current switches over completely to one side, and that point is, okay. Now the question is, what happens when it's in triode region? So the way we evaluate this point was, we say that one of the transistors is just at the verge of cutoff. Okay. So that means that the threshold voltage here is Vt. Okay. And the other transistor has whatever voltage is required to carry a current of I0. Okay. So what is that voltage? See, the philosophy is this: we want to make a switch. That is, if the input difference becomes something, it should switch. The current should switch completely from one side to the other side. Now, one quantity of interest is how much voltage difference is required to make the current switch from one side to the other side. The smaller it is, the more sensitive the switch is, the better logic gate it is. Okay. So we are interested in having smaller values of this one. Okay. Now, how do we evaluate this condition? For analysis, we look at the point where one of this is at the verge of cutoff, and we calculate how much voltage is required here. Okay. And from that we calculate the difference. Now let's assume that both transistors are in saturation. What is this voltage? So it's Vt plus 2I0 by mu Cox W by L, and the other one is Vt, so that's how we got this to be the switching voltage. Now let's say under this condition somehow this transistor was in triode region. What would be the voltage required here? Would it be more than this or less than this? Can you tell? You understand what I asked? So, okay. M2 is on the verge of cutoff. So, when it's just at the cutoff, M1 has to carry all of the current. Okay. Then we calculate the VGS of M1, VGS of M2, take the difference, and that's the switching voltage. Okay. VGS of M2 is clear. It's on the verge of cutoff, so it's Vt. Right. So, what is the VGS of M1? If it's in triode region. For it to carry all of the current I0. It has to be greater than this. Okay. Is everyone convinced that it will be greater? To carry a given current in triode region, you need a larger VGS. In saturation region, you need a smaller VGS. Okay. So if you simply look at the transistor characteristics, it looks something like this. So this is for VGS1, this is for VGS2 greater than VGS1, and this is for VGS3 which is greater than VGS2. Okay. Let's say we were interested in carrying this much current, I0. So in saturation you need VGS1. If it goes into triode region here, you need VGS2. If it goes into even deeper triode region, you need a larger voltage. Okay. As it goes deeper and deeper into triode region, you need larger and larger voltages. As the VDS gets small, the VGS has to increase to carry the same current. So based on that, so it will be not just this plus something. The expression may be complicated to calculate, but we clearly know that it has to be more than this. So what does it mean? So for this characteristic, the point where the current completely switches from one side to the other and will be farther out. Okay, so it will be a less sensitive switch. So that's why you don't want that. You want to have as good sensitivity as possible. The source potential lowers itself when it's in triode or saturation. No, both paths do conduct, right? When the input difference is 0, both are conducting. In fact, it's not a question of source potential lowering itself. The source potential will have to be whatever value is required for the current distribution. Okay. The gate voltage determines the source voltage. You are saying what will happen if this voltage lowers? But then, what are you assuming for the gate? They are at a fixed voltage? See, Kirchhoff's current law has to be satisfied. So let's say this voltage is equal to this. Each one is carrying a current I0 by 2. Okay. Then now, suddenly, if you imagine the same gate voltage and the lower source voltage, each of these will be more than I0 by 2. That is just not possible. Okay. So both do conduct. When it's not completely switched, both are conducting to different extents. So is it okay? The triode does this thing? Okay. So we have a multiplexer. Can we make any logic we want with this? Can we make an XOR gate? So it's quite easy, right? So what we have is, and if C equal to A bar, it's an XNOR gate, and you can always get the inversion simply by changing the wires. Okay. So what else can we make out of MUX? What else did we need for our serializer and deserializer? In fact, our discussion on these logic gates will be limited to what we want to do there, right? That's why we went to this discussion. We want to make serializers and deserializers at high speeds, and we found that CMOS logic is not the suitable family for high speeds. So we came to this. So we needed a multiplexer there, and we needed some logic elements like inversion and so on. All those things we know how to make. What else do we need? Latch. So how can we make a latch from this? How do we make a latch? What is a latch? What is the governing principle of a latch? How do you make like at the gate level, if I give you, let's say, a bunch of NAND gates, how would you make a latch? Back-to-back connection. So okay, how do you get the n-1? Actually, this is just a latch. There is no timing as such. Right? So latch is basically a memory element, and the way you get a memory element is by having positive feedback. Okay. So this is a self-restoring or whatever it is. So if you have a 1, that's 0, and then that 0 sustains a 1 and 1 sustains a 0. So as long as the power is applied, the states will be like this. Okay. Or unless you disturb it with some external means. Now, it's not enough to just have this. We also need a way to write the values into it. Okay. So that's why we use a gate. So we know that the NAND gate is an inverter if one of the inputs is a 1. Okay. We can do this, and by appropriately changing these two, we can change the state of this. Okay. So whichever side we want to write a 1, we pull that to 0, and that will go and get a 1. Okay. And when both of these are high, the state will be retained. Okay. So we need positive feedback. So how do we do that with our current mode logic gates? How do we implement this? The MUX have a feedback from output to input. Okay. So like don't we have to do this? Like we need 2 inverters to put in feedback. This is what we normally do. Why do we do this? Yeah, I know, I understand. Now, like the solution you are suggesting looks like we don't need 2 gates. Okay. So do we make 2 CML inverters and connect it in feedback? Why don't we do that? Yeah. In CML, you can get a positive feedback simply by inverting the wires. That's how you just. So if you had CMOS inverters, you would have needed 2 gates to invert it and make it positive feedback. In case of a CML gate, this kind of function can be realized by doing this. Okay. So now, what happens? So let's say this side is the lower side and this side is the higher side. And this is the higher side. That higher gate voltage makes sure that all of the current flows here, and this side will remain the lower side. So that is a positive feedback latch. So because you have both the inverting and non-inverting output available, you don't need explicitly 2 separate gates. Okay. So this is a latch, and the kind of latch we want is in what is the latch we want? When C has one polarity, we want this to go straight to the output. When C has the other polarity, we want it to hold the value that it had before. Okay. And this again is a multiplexer, right? So multiplexer meaning in one of the phases D should go to the output, in the other phase Q should go into positive feedback. Okay. And we have a multiplexer, so we can make the latch quite easily. And the positive feedback connection is easier to write if you flip the orientation of the transistor. So this is the latch, and you can see the cross coupling. This cross coupling is the positive feedback. Let me change my notation. I'll call this. So this is Q, and this is. So when CP is high, it's transparent. Okay, it's like a differential pair. M3 and M4 act like a differential pair, and QP and QN will be equal to DP and DN. Okay. And when CP is lower than CN, that is when this side is higher, it goes into positive feedback. So this differential pair is deactivated and whatever state was there will be held because of the positive feedback loop. Is this clear? So you have the control input and you have the one of the inputs in feedback from the output and the other one is the data input. Okay. So this is and how do we make a flip-flop? We just cascade two of these and reverse the orientation of the clock. To make, again here to change to invert the logic, it's quite easy. You just flip CP and CN. Okay. So to go from a latch which is transparent for positive clock to a latch that is transparent for negative clock, to flip CP and CN, and that's all you need to do. Okay. So we know how to make flip-flops. So with this, everything that we need for our serializer and deserializer can be realized at the transistor level. Okay. Any questions on any of this?